Log on, tune in, find out. Another good idea from Cambridge.
Okay, so the next speaker is Grant Passmore from Cambridge, and he will speak on decision methods over real and algebraically closed fields.
Okay, thank you very much for having me. Okay, so our work begins with an astounding theorem of Alfred Tarski. This theorem is as follows. The elementary theory of real closed fields admits effective elimination of quantifiers. So this was proved by Tarski originally in the 30s, wasn't officially written up until 1948, maybe, close to the 50s. But what does this imply? So this implies that the first order theory of the real numbers when seen as an ordered field and the first order theory of the complex number field are both decidable. Okay, so this is a rather marvelous decidability result given the huge amount of context we have of undecidability results in mathematics, especially when addition and multiplication are both involved. Okay. So this leads to a most tantalizing situation. In principle, because of these decidability results, every elementary arithmetical conjecture over real and complex numbers, finite dimensional real and complex spaces, can be decided simply by formalizing the conjecture and asking a computer of its truth. Right, so in principle, now if we have any conjecture, arithmetical conjecture, it's elementary, it's over finite dimensional real and complex spaces, we have an algorithm that we can formalize our conjecture, send our conjecture to this algorithm. The algorithm should be able to tell us whether or not this conjecture is true. So why then do we still have so many outstanding problems in elementary algebra and geometry over the real and complex numbers? So for instance, why do we still not know how many unit hyperspheres may kiss in 5 dimensions? It's known now to be between 41 and 44, but we don't know the precise number. And this is a problem such that for any fixed dimension and any number of hyperspheres, we can easily encode this as a problem over real closed fields. Well, the reason is an issue of complexity. So though decidable, the first order theory of real closed fields is fundamentally infeasible. So this is made precise by a landmark algorithmic complexity result of the 1980s by Davenport-Hines. This result says there exist families of n-dimensional RCF formulas. So RCF, this is the language of the structure of real closed fields, so it's also called the language of ordered rings. So there exist families of n-dimensional RCF formulas of length big O n, whose only quantifier-free equivalences must contain polynomials of degree 2 to the 2 to the big omega n and of length 2 to the 2 to the big omega n. So what we get out of this is that real quantifier elimination over real closed fields is inherently doubly exponential in dimension. So the hard part is scaling these decision methods to large numbers of variables. And large here could be 6 or 7 once we have doubly exponential bounds around. So it's interesting, in the wake of these complexity results, to recall Tarski's profound optimism when he first proved these decidability results. So this is from Tarski's paper that the official write-up of these results that was long delayed because of World War II, and eventually came out as a book published by the Rand Corporation. Very interesting story with how that happened, but the Rand Corporation was interested in how these machines for elementary real and complex algebra could be used for practical applications. So Tarski says as follows at the beginning of his book. Since a decision method, by its very nature, requires no intelligence for its application, it is clear that whenever one can give a decision method for a class K of sentences, one can also devise a machine to decide whether or not an arbitrary sentence belongs to K. Fair enough. It often happens in mathematical research, both pure and applied, that problems arise as to the truth of complicated sentences of elementary algebra or geometry. The decision method presented in this work gives the mathematician the assurance that he will be able to solve every such problem by working at it long enough. So I want to emphasize the long enough here. So Tarski's original procedure, of course this is before the advent of algorithmic complexity as a field as we know it today. Tarski's original procedure had non-elementary complexity. So the number of arithmetical operations required in general for a formula with n variables couldn't be bounded in advance by any tower of exponentials. So here we see, yes, so we can wait long enough, but we may have to wait until the end of the universe, per se. So Tarski's procedure is not interesting from a practical point of view, but of course this is a profound result that is, one of the longstanding hallmarks of mathematical logic, that these structures admit quantifier elimination. And now that we know this and we have decidability in hand, we can work to try and find practical algorithms. So that's what I'm going to talk about. So on the one hand, we now have that real quantifier elimination is hard, right? It's inherently doubly exponential in the number of variables. Yet, there are many examples, countless examples in mathematical and engineering practice of high-dimensional real closed field problems being solved. So what's the disconnect? Well, one explanation is that most high-dimensional theorems proved in practice are, of course, not proved by using a general decision method. They're proved by some ad hoc combination of methods, and these ad hoc combination of methods may be very tailored for the particular class of problems that your given conjecture fits into. The story is not so bleak as it might have seemed. Now we can ask, are all interesting fragments of the first order theory of real closed fields or the first order theory of algebraically closed fields of characteristic 0 infeasible? And the answer is no, thankfully. So I want to talk now about a dream, what many of us who work on these decision methods are hoping for, and that is we want to have some families of feasible decision procedures for practically useful fragments of the theory of real closed fields and the theory of algebraically closed fields of characteristic 0. So these are, of course, to us intrinsically mathematically fascinating, trying to isolate these fragments. And as we'll see, usually the complexity of these decision methods for different fragments really depend on the topological structure, real algebraic structure in the case of real closed fields, of the semi-algebraic sets, the sets of real vectors you're able to define within the fragment. So there's lots of interesting questions just about the procedures themselves and isolating the fragments. And there's so many applications. So I want to just now, as motivation, mention two classes of applications. So one is in pure mathematics. So here I have Thomas Hales. If anyone familiar with the FlySpec project? So this is a fascinating project ongoing now, started by Thomas Hales. So in 1998, Thomas Hales announced a proof of the Kepler conjecture on the densest way to, in this case, pack spheres in 3 space. And his proof relied on a huge number of computer calculations, much like the proof of the 4-color theorem did in the 70s. So he was able to break his proof down into a large finite number of cases and then develop specialized optimization algorithms to prove a large family of inequalities that corresponded to proving his theorem for each of these finitely many cases. For each of these individual inequalities, he was able to put them into special classes of inequalities based upon their structure and develop specialized algorithms that could attack them, that could prove these inequalities. So now it's a very, very difficult proof to verify, say, for a referee. From the perspective of the referee, you have, of course, the high-level mathematical strategy of the proof you can work through as we normally do. But then you have a huge amount of computer code, in this case code written in C or C++, some low-level languages that is doing these optimization calculations. And to really verify the proof, to know that the proof is correct, you have to not only check the high-level strategy, but also check all of these optimization algorithms. So it's a very difficult problem, and more these types of proofs, now, as we get more decision methods implemented and tractable for various fragments of mathematics, more proofs rely on computer calculations in this way. So Tom Hales has started a project called the FlySpec project, and the goal of it is to formally verify his proof in a foundational proof assistant. So the proof assistant of choice that he uses is one called Hall Light. It's a descendant of a system developed here called Hall in Cambridge. And there have been a number of recent PhDs on verifying pieces of his proof, and actually many of them in different proof assistants that have different logics. So this is motivating a lot of improvement to the field of formalized mathematics, and it's addressing questions as difficult as if you have a formal proof in one logic that is classical, a formal proof in another logic that is constructive. How can you in general combine these proofs for the fragments you're interested in? Lots of difficult questions here. And in particular, this conjecture, the Kepler conjecture, so Thomas Hales followed an approach outlined originally by Toth, and Toth was able actually to show that the whole Kepler conjecture can be encoded as a single, purely existential, real closed field formula. in over 200 variables. So for our doubly exponential and variable decision procedure, this is hopeless. Yet it fits into, here's an example of a deep problem in pure mathematics that you wouldn't perhaps naturally expect it, but actually can be encoded as a pure real closed field problem that only involves existential quantifiers. Okay, so that's one. So there's applications in mathematics, and especially in formalized mathematics, abound. Another class of applications comes from engineering and formalized for formal verification. Formal verification of engineering artifacts. Okay, is that bad? Yes. So here, this is a diagram that comes from what's called the Chimera project at Carnegie Mellon. And what they're working on is collision avoidance algorithms in unmanned aircrafts. So now it's quite scary in some ways. Now when you ride even in a commercial jet, very often, vast majority of the piloting is done by machine. So there you have, of course, hardware, and you have then huge amounts of software running on top of these things that are controlling the plane. And you would be amazed if you see diagrams of how many planes there are in the sky at any given moment. These things are quite frightening. So now a big push, as more and more flight control is made automated, there's a big push to actually formally verify, develop formal proofs of the correctness of these engineering artifacts, of core algorithms like collision avoidance algorithms in aircrafts. And when you do this, of course, you naturally derive large collections of high-dimensional geometrical conjectures that can be encoded as real closed field problems. And there we want scalable decision procedures for real closed fields that are useful, that can be applied. And in both of these settings, something interesting is because of the source of the problems, the problems themselves tend to have quite a uniform structure. So for instance, problems in both of these cases usually involve normal Euclidean distance. Well, our normal Euclidean distance formula is symmetric in every variable. So you have a lot of inherent symmetry in these formulas. So just using a blind general real closed field decision algorithm isn't exploiting this symmetry. There's many things you can do to try and develop specialized decision methods for classes of problems that arise in practice. Okay, so I want to give an example of such a fragment. So if we focus on just the existential fragment of the theory of real closed fields of characteristic 0, there's an approach that's very different than full quantifier elimination, and that's an approach based on Grosvenor bases. So I want to just give you a quick sketch of what Grosvenor bases are. So let's say we're given a collection of k polynomials in the polynomial ring q x1 to xn. Key point is that we have finitely many variables, and so by Hilbert's basis theorem, our ideals are all finitely generated. So now, what's an ideal in this case? So an ideal generated by P1 to Pk, it's just the sum of products of our basis elements, that's what we call those Pi's, and arbitrary elements of the polynomial ring Qi. So that's the ideal generated by P1 to Pk. So what are ideals? Of course, ideals are an algebraic generalization of nullity. They're the kernels of our ring homomorphisms. And in this case, as I said, this collection of polynomials is called a basis of this ideal. But unlike linear algebra, there's no notion or immediate notion of canonicity for a basis. So for instance, if we add to this P1 to Pk another polynomial that's implied to be in the ideal, for instance, if we add in P1 plus Pk, we can get another basis for the same ideal, right? So there's no notion of canonicity like there is for vector spaces. So one approach to getting canonicity is called Grosvenor bases. I'll talk a bit about them. So Grosvenor bases are very useful for the following problem, and that is deciding ideal membership. This problem takes the following form. Given a polynomial s in our polynomial ring, again we have finitely many variables, and an ideal I, which is generated by P1 to Pk, is S a member of the ideal? This is a natural problem that arises in many areas of mathematics. That's equivalent to saying I'm given a ring homomorphism that's induced by this ideal from our original polynomial ring to the quotient ring, where we quotient by the ideal I, and does this homomorphism map our polynomial to the equivalence class of 0? Okay. So this, of course, admits an algorithmic solution, but it admits an algorithmic solution of a very different form than full quantifier elimination. So it's maybe easier looking at these from the perspective of a decision problem to phrase this as a question of complex satisfiability. So solving satisfiability, SAT, for nonlinear complex arithmetic, we're given problems of the following form. We have a finite conjunction of polynomial equations. We can, of course, always zero the right-hand side. So we have some collection of polynomial constraints. P1 to Pk are all equal 0. These are, again, in our same polynomial ring. We want to know, do there exist complex values of the variables that satisfy this constraint system? Well, Hilbert's weak Null-Stellensatz reduces set for complex arithmetic to ideal membership. So Hilbert's weak Null-Stellensatz tells us the following. The collection of complex vectors which satisfy our formula is empty if and only if one is a member of the ideal generated by the polynomials. So in a sense, as ideals are a generalization of nullity, this tells us, Hilbert's weak Null-Stellensatz tells us something very, very magical, and that is that the only way you can fail for your system to be unsatisfiable over the complexes is if your system of polynomial equations in a very simple way implies that 0 equals 1. Because this, of course, is a generalization of being 0, and now we're saying 1 is inside of it. So it's a very, very simple type of syntactic refutation. Okay, well, how do we solve the ideal membership problem? So we see before, point of showing you this, is that this decision problem reduces to ideal membership, right? So we want to know, is this system of polynomial equations satisfiable over the complexes, and that reduces to ideal membership via Hilbert's weak Null-Stellensatz. So this can be solved using Grosvenor bases. The main idea is as follows. We can fix an order on our monomials in our polynomial ring. So our monomials, the order for them is a total order, and it must be what's called admissible. This just means it has to respect multiplication in a natural way. Once we do this, every polynomial will have a head term. So this is the term that's maximal with respect to our ordering. I'll underline it. So this now induces a rewrite system. Each polynomial gives one rule. So if this is our head term, we now have a rewrite system induced by this polynomial where m1 will say rewrites via p to the following. And all I've done is move the coefficient of m1 over. And the important thing to remember is we're talking about these p's with respect to forming an ideal. So there's an implicit equals to 0 here. So we move everything else over to the other side, and then we divide by our coefficient, and that's how we get this rewrite rule. Okay, so given an ideal I, a Grosvenor basis for I is a basis, so it's a collection of polynomials in our same polynomial ring, and it's a basis for our exact same ideal I, such that the rewriting system generated by this basis is confluent. So what does that mean for us? That means that ideal membership can be checked simply by rewriting. Okay, so to give an example of the kinds of things that I'm working on, right, there's many different approaches to computing Grosvenor bases, many different algorithms. There's the sort of dominant paradigm is based on Buchberger's algorithm, Buchberger being one of the two originators of Grosvenor basis, Grosvenor-Shirshov basis. And right, so there's many different approaches, and for particular classes of problems, algorithms based on Buchberger's algorithm are not effective. And so in my PhD, one of the things I worked on was developing algorithms for specific classes of polynomial systems that Buchberger's algorithm would fail to solve in feasible amounts of time. And so to do this, what I ended up doing, together with my collaborator, Leonardo de Mora, we developed what we call the abstract Grosvenor basis calculus. So this, in a sense, is I think of it as the sort of machine code for Grosvenor basis algorithms. So it's a collection, a very small collection of inference rules that can be seen as the primitive operations that a Grosvenor basis algorithm needs. And then we defined a notion of a correct strategy, which is a computable sequencing of these rewrite rules. And for a strategy to be correct, there's a very, very simple local notion of correctness that's quite easy to check. And we were able to prove that if you are, in our sense, a correct strategy for sequencing these rules, then you correspond to a Grosvenor basis algorithm that's sound and complete. In the process, we showed that a number of classical Grosvenor basis algorithms are each instantiations of this abstract Grosvenor basis calculus. And so what this gives us, I mean, just to give you an idea of the kinds of things we're working on, is there are many optimizations for Grosvenor basis algorithms that are effective for different classes of problems. And what we're especially interested in is when these optimizations that are motivated by a particular class of problems could actually be used in Grosvenor basis algorithms in general, or in a large class of Grosvenor basis algorithms. So a big thing we try to do is find techniques that can improve the calculation of these Grosvenor bases and actually prove that these techniques are correct with respect to any correct strategy. So if they're correct with respect to any correct strategy, then we get them for free for all of our Grosvenor basis algorithms, instead of just our particular one that motivated them. So that's something I worked on. My PhD was proving what I call the strategy-independent admissibility of a few of these approaches. Okay, so that's just an idea for algebraically closed fields. I want to talk to you a little bit about something that we're working on over real closed fields. So over real closed fields, of course, we have we have more types of constraints because we have ordering. So the real closed fields form an ordered field. This ordering makes the topological structure of the sets we can define quite different. In particular, we talk over real closed fields of semi-algebraic sets, which are the collection of vectors of real numbers which satisfy a quantifier-free formula in the language of ordered rings. And what quantifier elimination, what Tarski's theorem tells us, is that semi-algebraic sets, the collection of them, is closed under projection. Okay, so Tarski's algorithm is non-elementary in complexity, the original decision algorithm for real closed fields, and a number of others have been developed since, well, many of them aiming at making the real closed field problem more feasible. So one was developed by Paul Cohen, which was actually also had non-elementary complexity, but was a lot perhaps simpler to understand than Tarski's. Another developed by Muchnik independently that's very similar to Cohen's. And Cohen's method was also extended by Hormander. And coincidentally, I'm giving a course right now that started today on Muchnik's methods. Muchnik's quantifier elimination is very interesting because it's a uniform method that, with very small alterations, works over algebraically closed fields of characteristic 0 and real closed fields. So with just some small changes, the general Muchnik machinery can be made to work in both settings, which is quite neat. But now the dominant paradigm for quantifier elimination over the reals is called CAD, cylindrical algebraic decomposition. This was given by Collins in the 70s. And so CAD is an overloaded term. It's both a type of decomposition of Euclidean space, and it's the name of an algorithm, and it's the name of the key data structure of that algorithm. So I'll try to use it in ways that are understandable. But what is CAD abstractly? So a CAD is a decomposition of Euclidean space, R to the n, into finitely many semi-algebraic connected components, which behave, in a sense, nicely with respect to projections. So they have to be what's called delineable. But the point of a CAD is if I'm given some finite collection of polynomials, again in, say, this exact same polynomial ring, I can compute what's called a p-invariant CAD. And what a p-invariant CAD is, it's a CAD, so it's a decomposition of our Euclidean space, but it's one that's induced by these polynomials in the following sense. Once I have this decomposition of Euclidean space into finitely many semi-algebraic connected components, so let's call each of these connected components Ci, I now have the following property. Given any component Ci and given any polynomial in my set P, my polynomial has constant sign on every member of this cell. That's the key property that allows CADs to be used for making real algebraic decisions. So for instance, if you have a purely existential formula, well, what does this tell us? Well, we can take our formula and see in our purely existential formula is just a collection of sign conditions, because I can just zero the right-hand side of all of my atoms in my formula. Now, every atom is just asserting that a given multivariate, potentially, polynomial has a sign. It's either greater than 0, less than 0, or equal to 0. And now, if I have a decomposition of my Euclidean space such that all of my polynomials in my input formula have constant sign, well, all I have to do to decide satisfiability is pick a sample point in each cell and check my formula on each sample point. Because this is a partitioning, it's a full cover of R to the n, that's sufficient. Okay, so this can be made to work. This can be made to work for formulas also with quantifiers. So I wanted to give, this is a nice diagram of CADs produced by Chris Brown, who's a CAD researcher who works on a particular CAD implementation called QEP CAD. And this is an example of, so CAD is built by induction on dimension. You start with your multivariate polynomials, project them down into a set of lower dimension, keep going, you eventually get a set that's purely univariate. You can isolate the roots of those univariate polynomials. That induces a CAD of one-dimensional space. Then you can build a CAD for the next dimension using your polynomials that appear in just one more variable. by building building what's called a stack. You're building a decomposition of your next dimensional space that is done just locally for each of the cells for your lower dimensional space. So it has a very nice inductive structure. Now, CAD is doubly exponential in dimension, and the algorithmic complexity and practice of CAD algorithms are highly dependent on the topological structure of the real algebraic solution set induced by the polynomials in your formula. So another thing we're working on, motivated by this, is trying to isolate fragments of RCF for which we can find variants of CAD algorithms that perform better than CAD does in general. And so one fragment that I worked on in my PhD is a variant for formulas in which every variable is compactly bounded. And what I do is I combine Grosvenor basis calculations, so some computations over the complexes, together with a variant of CAD that only lifts over what are called full dimensional cells. So at any given stage in building a CAD, you have some collection of cells, and these cells are homeomorphic to, if you're at dimension I, your cells are homeomorphic to R1, R2, R3, or all the way up to Ri, homeomorphic to one of those subspaces. And in full dimensional CAD, you only lift over cells that have the same dimension as your current inductive step that you're on in the CAD construction. And so what this means in practice is if you do full dimensional CAD, you never have to compute with irrational real algebraic numbers. You only have to compute with rational numbers. You never have to select cells, sample points from cells that don't contain rationals. You're always selecting them from full dimensional cells, and full dimensional cells are always open sets in this case. And so you can always select rational sample points. And that makes CAD much more tractable for particular classes of problems. So that's the kind of thing we're trying to do. And another thing is incomplete heuristic procedures. So there's no doubt that incomplete heuristic procedures are extremely useful. So for instance, Thomas Hales has developed a large battery of techniques to attack different fragments of RCF problems which are needed in his proof of the Kepler conjecture. And in doing this, he uses many techniques that are known to be sound, but they're certainly not known to be complete. And I like to say we want to use these early and often. We want to be able to use these techniques that are practically useful before we understand which fragments they are complete for. So that motivates the following question. How can practically useful, sound but incomplete RCF proof methods be systematically utilized in the context of a complete RCF proof method without sacrificing its completeness? So then, to try and address this, I developed something called abstract partial CAD in my thesis, and this is a higher order CAD-based decision algorithm that accepts arbitrary sound but possibly incomplete proof procedures for the existential fragment of real closed fields and uses them as functional parameters for trying to short circuit some expensive computations during CAD construction. So this is implemented in a system that I developed called RAD, real algebra in high dimensions. And a property of RAD is that these real closed field proof procedures are first-class objects inside of RAD. So RAD has a language with inferential primitives, which are consist of many different RCF and ACF0 proof methods, and has a strategy language for combining them to build heuristic proof procedures. And these become first-class objects that can be passed to each other. And that's how this abstract partial CAD can be implemented. So you get a higher order CAD that can take as parameters an arbitrary sound but possibly incomplete proof procedure for the real closed fields and use it to short circuit some expensive computations. So this is just an example of one of these strategies, or one of these heuristic RCF proof methods expressed in RAD. This one combines Grosvenor basis calculation and full dimensional CAD, and this can be then passed to a higher order CAD algorithm, and it will use this to try and short circuit things. So this is the type of analysis that we get out and that we focus on to try and find, okay, did doing this particular type of RCF reasoning help for this class of problem? How many full dimensional semi-algebraic cells was I able to eliminate just by using this type of reasoning, and so on. So we're trying to develop practically useful proof procedures, and so we have to do a lot of sort of engineering to try and implement these things well and find ones that are useful in practice. Okay, so in conclusion, RCF and ACF0 are decidable but infeasible. General methods will not suffice for practical use. So instead, we need to isolate and implement feasible decision methods for various useful fragments of these theories. The MO that I tend to follow is to get problems first from people that fall into either the theory of real closed fields or the theory of algebraically closed fields of characteristic 0, and then try to develop proof methods for them. Because in general, a full proof quantum fire elimination method isn't going to be tractable, and it's very difficult to know which fragments to focus on unless you have problems first. So that is to say, if you do have problems that arise, please send them to me, and I would love to try to work to develop procedures that solve them. And we need methods, talking about ongoing work, we really need methods for incorporating the use of practically useful, heuristic, sound but incomplete proof methods in the context of complete methods in a way that doesn't sacrifice the completeness of the combined method. So this abstract partial CAD that I talked about is one initial approach, but this is in its infancy, and much more needs to be done for these to bear practical fruit. Okay, thank you.
Are there any questions?
So, are there specific, real closed fields? There are countable real closed fields, there are real numbers, there's a lot of others. You have in mind any particular computation method here?
Oh, yeah, so here we rely heavily on, we really compute over the real algebraic numbers.
Real algebraic numbers.
So this is the sort of...
No transcendence, but yeah.
That's right, yeah. So from the goggles, the perspective of the language of ordered rings, every real closed field is elementarily equivalent. Any two are elementarily equivalent to each other, right? And so RCF is a complete theory, and so then the algebraic reals form a real closed field, and in particular they form one where the operations we need are computable.
Okay. Operations such as
having
things like finding square roots, finding cube roots?
Yeah, well, it's things like evaluating a polynomial at a given real algebraic number and computing its sign.
That sounds plausible.
That sort of thing. So that's
in pretty much any context that should be feasible.
that's key.
Right?
Yeah. So here, sign determination is really key. So the core of algorithms like CAD are, there's many subcomponents, but a core one over real algebraic numbers is, for instance, deciding the sign of a univariate polynomial evaluated as a real algebraic number. A common way to present real algebraic numbers is as a minimal polynomial together with an interval that contains only one root.
Right.
So that's your sort of normal representation method. That answer your question?
For now, we can. I'm very jet lagged right now.
Okay.
There are no other questions. One thing which I forgot to ask Albert also was to ask him how long he is around. So, but maybe first we ask you. You are here in Cambridge, so you should be around all the time.
Yes.
So for us, no problem to ask other questions later. Albert, how long are you here?
I'm here until February 21st.
Oh, that's also very long period. So February 21st, if you want to discuss anything with us. Let's thank Grant again for his nice talk.